Hi, this is the Emergency Preparedness Team. I'm Adelene.
I'm Alison.
I'm Eashan.
I'm Grady.
I'm Joel.
I'm Natasha.
I'm Neha.
I'm Sabrina.
I'm Sophia.
And I'm Sheryl.
In 2020 alone, 416 natural disasters such as fire, extreme heat, and flooding occurred. In addition, natural disasters are on the rise, with the number of yearly disasters increasing. There is some evidence to suggest that climate change may cause even more extreme weather, in which case these problems will only get worse in the future. Many of us have personally witnessed natural disasters firsthand, whether it was the storms in Texas or the wildfires in California. As a result, all of us know how important it is to prepare and prevent emergencies. Different data and algorithms can be used to more effectively predict natural disasters, identify steps we can take to reduce the impact of them, and assist response teams like Red Cross or FEMA.
So what is remote sensing? Well, remote sensing is the process of using spacecraft and satellites with specialized sensors in order to collect data about the Earth. Different satellite sensors collect data from different EM waves or collect data at different time intervals. And what are its uses? Well, we can access this data through tools such as Google Earth Engine in order to make models so we can accurately predict the future.
To access and analyze remote sensing data, we use Google Earth Engine. Google Earth Engine, or GEE, is a free remote sensing data analysis tool open to the public that provides over 30 years of satellite imagery and geospatial datasets that are ready for analysis. By using cloud computing capabilities, GEE allows for automated data processing, machine learning algorithms, GUI applications, and other tools to display analysis results. Our team used both the Earth Engine JavaScript API through GEE Code Editor and the Earth Engine Python API through Google Collaboratory or Colab.
We use NASA's Applied Remote Sensing Training Program, or RSEP for short, to facilitate our learning in Google Earth Engine. The RSEP program consists of a series of training sessions used to train viewers in a wide variety of datasets and tools which relate to specialized environmental applications. Across our group, we watched 11 RSET sessions relating to the topics of Google Earth Engine, population, fires, urban heat, blackouts, tropical storms, and flooding. Viewing these sessions heightened our proficiency in Google Earth Engine and allowed for us to make deeper dives into our topics.
Our primary methods of data visualization were through creating maps and time series. So in order to map our data set, we would first import the Earth Engine API and GE map package. Then we would add and filter our data set by date, band, and more. Thirdly, we would select our area of interest, and then we would select the visualization parameters based on the band. Finally, we would add the map layer and display the map. Some additional features we could use were legends, multiple map layers, and clipping. And we'll talk about that in time series later on.
After our RSET training, we selected our areas of interest and divided into 3 subgroups: extreme heat, wildfire, and tropical storms and flooding. Throughout the entire process, our mentor, Ms. Howard, helped us with different code and provided valuable feedback. Thanks, Ms. Howard.
Extreme heat is characterized by high temperatures and humidity extending over several days. It causes heat exhaustion and dehydration, which is lethal if not treated quickly. Extreme heat is often found as a symptom of urban heat islands, metropolitan areas where human development and geography have contributed to higher surface and air temperatures than surrounding suburban and rural areas. Our goal is to analyze models of surface temperature in and around urban centers to determine whether geographical features and certain human activity impact the extent of the urban heat effect. Using our results, we created a list of heat mitigation strategies for cities to better prepare and prevent extreme heat.
We use land surface temperature measurements from MODIS and Landsat 8 to quantify the temperature difference between urban heat islands and their surroundings. Despite the precision of atmospheric temperature measurements, we're using land surface temperature data due to its wider availability and ease of interpretation. Measurements of surface temperature are completed using remote sensing satellites, whereas similar atmospheric measurements would take a plethora of different spread out observation stations and labor. To account for the sometimes sporadic nature of these land surface temperature measurements we use both 30-meter resolution Landsat 8 data and the 1,000-meter resolution MODIS data to verify any anomalies such as temperature spikes when not expected. The differences between these resolutions and the data can be seen in the figure on the slide, which shows the same area on the 2 different data sets.
These 2 images depict San Francisco, with the land surface temperature image on the left and the NDVI, or Normalized Difference Vegetation Index, image on the right. NDVI is used as an indication of vegetation density. Using these two images, we can see that vegetation is a major factor in lessening the effects of urban heat islands, as it lowers surface albedo. Almost all of the cooler areas on the land surface temperature image correspond to areas with higher vegetation density on the NDVI image. However, we can also see that the vegetated sections of the city don't have a cooling effect beyond their immediate area. For instance, the cooling effects of even the most dense area of vegetation there on the middle left don't extend far beyond the area's limits. That short range of cooling can also be seen in the green areas on the far bottom, far top, and the Golden Gate Park. This shows two things. One, that urban areas need to be better planned so as to allow for vegetated areas everywhere. The east side of the city, as well as the area below the Golden Gate Park, have almost no vegetation and thus are very hot. Two, that instead of having a few large areas of vegetation, cities need to have many smaller areas distributed evenly across themselves. Because vegetated areas only have an effect in their immediate vicinity, having many smaller areas covering the city should be a viable way to reduce the urban heat island effect everywhere. Most urban areas would have a vegetated area near them, as opposed to only a few in the current situation.
As presented in the data, the severity of the urban heat island, or UHI effect, varies greatly across the city of San Francisco. Surface albedo, surrounding terrain, and energy use all play a role in the development of UHIs. The increased temperature caused by UHIs can have drastic consequences for human health, such as causing heat strokes, increasing the concentration of air pollutants, and exacerbating pre-existing health conditions. However, there are ways to combat the urban heat island effect. Government agencies can introduce regulation on vehicle manufacturers to reduce the emission of compounds that contribute to urban smog. By reducing smog, heat is less likely to be trapped around urban areas. City planning officials can promote the implementation of green roofs and create areas of tree cover and create green belt zones as ways of increasing city surface albedo, which lowers surface temperature.
We decided to use Google Earth Engine to examine wildfires in California. Both of us are residents of California and have had to evacuate during wildfire seasons in the past, making us interested in how wildfires affect the populations in California. Using a population dataset, WorldPop, and the Modus burn area dataset, we created two images of California's burn areas and population in 2001 and 2020, which shows an increase in burn scars.
After looking at 2001 and 2020, we wondered how many people were directly affected by wildfires over the years, so we examined California from 2000 to 2020. We used the same two datasets, the WorldPop dataset masked by the Modus burn area dataset, to get the total population affected each year. The calculated values in this graph only include people who lived directly where fires burned, but in reality, many more people were affected by the worsened air quality and the evacuations. After plotting our calculated values on this line graph, we created a line of best fit, the orange line, to examine any trends. Although the line of best fit shows an increase in population affected by wildfires over the years, there are some notable outliers. For example, in 2003 and 2007, intense Southern California wildfires were driven by the dry Santa Ana winds and dry conditions due to drought. In 2017, record precipitation and increased vegetation was followed by intense heat, which created fuel for wildfires. Finally, in 2018, record warm weather and lower than average precipitation extended the wildfire season. All of these factors led us to wonder how we might predict where another major fire could occur. Therefore, for our main project, we created a fire risk map for California. We decided to focus on 5 main factors that might make the region more vulnerable to wildfires: high vegetation used as fuel, high wind speeds, high temperatures, low humidity, and certain topographic features. Although there are many other factors such as drought or past fire history of an area, we focus mainly on analyzing and combining data about these 5 factors. We used the USGS Landsat 8 dataset and the NLCD USGS National Land Cover dataset to look at vegetation levels and land cover classification. We also used the University of Idaho's GridMet dataset to map wind speeds, temperature, and humidity. Finally, the USNED landforms dataset was used to map topography and landform classification.
Here's an overview of the algorithm we used in our risk map. In Figure 1, we show an example of our risk scoring, specifically for vegetation. Using Landsat 8 data, we calculated the Enhanced Vegetation Index values for California. EVI values range from 0 to 1, with high values describing greener vegetation increasing wildfire risk. We placed the EVI values into 4 estimated tiers, with the lowest tier having a risk score of 0 and the highest of 3. This resulted in a simplified map to the right of the arrow. Vegetation was not the only factor we looked at. Regions that have humidity below 15%, high wind speeds, sloped areas, extreme heat, and shrublands are more susceptible to wildfires. Then we used a similar scoring system on each of the 5 other factors.
We then added all the simplified datasets to create our final risk map. This means that a single pixel's value in the resulting risk map is the sum of its value in the 6 simplified datasets. With the completion of our risk scoring, we put together this final fire risk map. The dark blue areas have a low risk for wildfires, while the bright green areas are the most susceptible to wildfires. On the left side is a close-up of the Bay Area.
To analyze our result, we compared our fire risk map with the California population dataset and with burn scars from 2020 wildfires. On the left, we mapped the population dataset to examine communities and their risk for wildfires. Although many developed areas are marked as less risk, human presence may actually raise the risk of human-caused fires. On the right, we mapped the MODIS burned area dataset, and in the future, we want to conduct an in-depth analysis of how useful our risk map is. But this initial comparison reminds us that our risk map, using only 5 factors, can only predict the vulnerability of an area. However, we still saw that many burn scars were located in or around areas marked as high risk in our map.
We decided to focus on the regions of Florida and Puerto Rico and the general Caribbean area due to recurring hurricanes and tropical storms. Specifically, we focused on Hurricane Irma and Hurricane Maria, which occurred in the same year and caused devastating impacts to housing areas and vegetation in the general Caribbean area. Hurricane Irma had the strongest wind speeds worldwide in 2017, and both hurricanes suffered from massive power outages, and these vulnerabilities were mitigated by critical food and relief training and programs. Here are the datasets we chose in relation to tropical storms and flooding.
Another data visualization technique we use with time series. A time series is a collection of data points correlating with time, and it can be represented as line charts, animations, and more. To go from the Earth Engine dataset to a chart, we have to reduce the image collection and then convert to a manipulable pandas data frame so that we can graph it. So after selecting the dataset and area of interest, we need to reduce the dataset's image collection of that region. And then we can convert to a Python dictionary and then a pandas data frame. After that, we can graph the data using matplotlib and seaborn libraries. So after conducting a time series analysis of surface soil moisture and precipitation, we found a general soil moisture and precipitation peak in the fall hurricane season, which means flooding from hurricanes during that time is more likely to happen due to the generally higher concentrations of moisture in water.
Adding on to Adeline's time series, here are the maps for the precipitation and soil moisture data sets with a focus on Florida and the Caribbean. You can see here that there are similar correlations between precipitation and soil moisture, where the greatest areas of precipitation shown in red generally appear in the same areas with the greatest soil moisture, also shown in red. Both properties are important determinants for tropical storms and floods, which is why mapping it out allows us to recognize the patterns of the disasters that strike. A tool to connect the two maps together is through overlapping the maps, by isolating the greatest values of the two and masking them together so we can clearly identify the areas with both the greatest values of precipitation and soil moisture. As seen here, the areas covered in black represent the areas that have both high soil moisture values and precipitation values, areas in which were severely devastated by the hurricanes. To overlap the maps together, we will go through an example with soil moisture and flooding. First, we isolate the pixels from the datasets that we want to mask together. The GTE function allows us to retrieve all the soil moisture values that are greater than or equal to 0.8 and update the soil layer to mask only those values. The resulting map on the right demonstrates the isolation process, where we can only see the areas with high soil moisture in red, with no more yellow, green, and blue values in the layer.
Just like in step 1, we must isolate the data we want to overlap from dataset 2. Since the flooded band in the Global Flood Database includes permanent water, we have to subtract it from the raw data to isolate flooded areas, as shown here. Now we can overlap the two datasets. Since they now consist only of binary values, areas of overlap are areas where pixels from both datasets are equal to 1, which we isolated by masking dataset 2 onto dataset 1. So the black areas represent the overlap between high soil moisture and flood areas. Here's an example of overlapping flood areas with high precipitation and with dense population. This method allowed us to highlight areas at risk of flooding and identify vulnerable populations in our area of interest, as shown in black. From our research, we have found that time series and overlapping are valuable methods for analyzing floods and tropical storms, especially because of their adaptability. They also allowed us to find strong correlations between different data sets. In the future, we would like to combine all of the data sets into one comprehensive flood risk map like the one from FEMA shown here.
NASA's ARCHA training guided us in understanding the Google Earth Engine environment and tools to successfully dive deep into our project using the functions mentioned in the webinars and methods to analyze natural disasters. We also converted JavaScript to Python in Google Colaboratory for data manipulation. Our future interests include exploring black marble nightlife data to integrate into our project. During the SEEDS internship, our 3 subgroups each focused on a specific topic area in extreme heat, wildfires, and plus tropical storms. And you can see our map displays made with Google Earth Engine. Lastly, we have included a link to our comprehensive work for future emergency preparedness groups.
Getting to know everybody was definitely the highlight of it. I don't really get to interact personally with a lot of people that have a similar interest in science, so this was a nice change of pace.
My highlight was being able to work through all the code with my team members and Mrs. Howard. We individually found code problems overnight, and then we would meet to solve them together. It was also fun to connect over other topics. I found I really enjoy working in a collaborative setting, and I'm excited to do so as a future engineer.
After learning about GEE through NASA's ARCA training, we were able to develop our own algorithm in the wildfire subgroup. Initially, this seemed to be a daunting task, but we were able to complete it once we recalled what we learned through the GEE training, as well as read through GEE documentation. Once we were able to see our results, it was very rewarding.
The biggest challenge I faced during the internship was finding a direction to go in with my team. Google Earth Engine had so many amazing data sets and methods available to us that it took a while for us to make sense of all of them in order to find a concrete direction to go in for our presentation.
The most important lesson that I've learned from the SEEDS internship is the significance of asking questions. Coming into our first few meeting, I was initially afraid to ask questions in a large group setting due to fear from imposter syndrome. However, as we transitioned to subgroups, I clarified technical jargon, data analysis methods, and confusions I had with my team members and Ms. Howard.
The biggest lesson that I've learned from this year's SEAS is the importance of relationships and friendships. When I first came into this team, it was honestly pretty scary, just having like 9 other people sitting on Zoom and not really knowing them. And yeah, but like once we started really working on the project and talking and joking, talking about things outside of SEAS, then meetings became much more enjoyable, and I think I definitely learned a lot more.
The SEAS program has inspired me to further develop my passion in computer science and has introduced me to its importance in earth science and remote sensing research. It was so exciting to be able to work alongside students from all over America and be able to apply all the geospatial tools we learned when analyzing satellite data sets.
This experience has given me the chance to apply computer science, a major interest of mine, to earth sciences. After learning about remote sensing, I now have a clear sense of how we can use technology to prepare for natural disasters. So in the future, I hope to continue to explore the uses of programming and remote sensing in earth sciences.
SEAS has given me the opportunity to solidify my plan to pursue computer science, as well as sparked a new interest in earth science and interdisciplinary research that I hope to explore further in the future.
For me, a big highlight was getting to meet and interact with people from all over the United States that are very talented. Even while working, we had a few lighthearted moments, so we got to know each other and work better as a team.
Here are all the resources we used from the heat, wildfires, and floods and tropical storms research. To conclude, we'd like to thank all the partners from the SEEDS program for this wonderful opportunity. Thank you, Ms. Miller, Ms. Badger, and all the speakers who were part of the speaker series for organizing the program and sharing your experiences with us. And a special thanks to our fantastic mentor, Ms. Howard, for guiding us through our project and introducing us to the world of remote sensing. We are all so happy to have taken part of the SEEDS program and cannot wait to apply the skills that we have learned into our future plans. Thank you all so much.